2I/Borisov, originally designated C/2019 Q4, Borisov, is the first observed interstellar comet and the second observed interstellar interloper after Oumuamua. 2I/Borisov has a heliocentric orbital eccentricity of 3.3 and is not bound to the Sun. The comet will pass through the ecliptic of the Solar System in December 2019, with the closest approach to the Sun at just under 2:00 on December 8, 2019. Nomenclature. The comet is formally named 2I/Borisov by the International Astronomical Union, IAU, but is sometimes referred to as Comet Borisov, especially in the popular press. As the second observed interstellar interloper after 1I/Oumuamua, it was given the 2I designation, where I stands for interstellar. The name Borisov follows the tradition of naming comets after their discoverers. Before final designation as 2I/Borisov, the object was referred to by other names. Early orbit solutions suggested that the comet could be a near-Earth object and was thus listed on IAU's Minor Planet Centers, MPC, Near-Earth Object Confirmation page, NEOCP, SGB 00234. Further refinements after 13 days of observation made clear the object was a hyperbolic comet, and it was given the designation C/2019 Q4, Borisov, by the Minor Planet Center on September 11, 2019. Astronomers such as Davide Farnaccia, Bill Gray, and David Tholen were already confident that the comet was interstellar. On September 24, 2019, the IAU announced that the Working Group for Small Body Nomenclature kept the name Borisov, giving the comet the interstellar designation of 2I/Borisov, formally announcing the comet was indeed interstellar. Characteristics. Physical characteristics. Unlike Oumuamua, which had an asteroidal appearance, Borisov's initial observations and subsequent third-party validation affirmed the presence of a coma around the body, indicating a cloud of dust and gas that would classify the body as a comet. Dave Jewett and Jane Liu estimate from the size of its coma the comet is producing 2 kg/s of dust and is losing 60 kg/s of water. They extrapolate that it became active in June 2019 when it was between 4 and 5 from the Sun. Initial estimates for the size of 2I/Borisov's nucleus, published on September 12, 2019, ranged from 2 to 16 kilometers, based on observations made by Karen Meach at the University of Hawaii, while Guzik et al. Estimated a size of about half a kilometer, assuming an albedo of 0.04. On 18 September, Siraj et al. Argued that the nucleus was likely small, on the order of 2 kilometers. An improved size estimate, based on the production rate of certain molecules in the comet's coma, was published by Alan Fitzsimmons, Karen Meach and others on 26 September. They estimated that the nucleus is between 1.4 and 6.6 kilometers in diameter. On September 13, 2019, the Gran Telescopio Canarias obtained a preliminary, low-resolution, visible spectrum of 2I/Borisov that revealed that this comet has a composition not very different from that found in typical Oort cloud comets. Similarly, measurements taken at the Nordic Optical Telescope found the comet had color indexes resembling the Solar System's long-period comets. The William Herschel Telescope, located at the island of La Palma, reported the detection of cyanide, formula CN, emission at 388 nanometers. This type of emission has been detected in many other comets, including Comet Halley, and put constraints on the production rate of other molecules such as diatomic carbon, formula C2. This was the first detection of gas emissions from an interstellar object. Later observation at the Bok Telescope and MMT Telescope in Arizona detected diatomic carbon. The ratio of C2 to CN is similar to a depleted group of comets, most of which are Jupiter family comets. The comet will come within about 2.0 of the Sun, a distance at which many small comets have been found to disintegrate. The probability that a comet disintegrates strongly depends on the size of its nucleus. Guzik et al. Estimated a probability of 10% that this will happen to 2I/Borisov. Jewett and Liu compared 2I/Borisov to C/2019 J2, Another comet of similar size that disintegrated in May 2019 at a distance of 1.90 from the Sun. If 2I/Borisov disintegrates, it is possible that it leaves behind an inactive remnant, similar to Oumuamua. Trajectory. As seen from Earth, the comet is in the northern sky from September until mid-November. It will cross the ecliptic plane on November 13, 2019, entering the southern sky. On December 6, 2019, the comet will be an equal distance of 2.0 from the Sun and Earth. On December 8, 2019, the comet will come to perihelion, closest approach to the Sun, and will be near the edge of the inner asteroid belt. In late December, it will be about 1.90 from Earth and have a solar elongation of about 80 degrees. Due to its 44 degrees orbital inclination, 2I/Borisov does not make any notable close approaches to the planets. 2I/Borisov entered the solar system from the direction of Cassiopeia near the border with Perseus. This direction indicates that it originates from the galactic plane, rather than from the galactic halo. In interstellar space, 2I/Borisov takes roughly 9,000 years to travel a light year relative to the Sun. It will leave the solar system in the direction of telescopium. 2I/Borisov has passed within 5.7 light-years of the binary star system Kruger 60, 13.18 light-years away, in Cepheus, at a low velocity of 3.4 km per second around a million years ago. 2I/Borisov's trajectory is extremely hyperbolic, having an orbital eccentricity of 3.3 to 3.4. This is much higher than the 300+ known weakly hyperbolic comets, with heliocentric eccentricities just over 1, and even Oumuamua with an eccentricity of 1.2. 2I/Borisov also has a hyperbolic excess velocity, \displaystyle v_\, of 32 km per second, much higher than what could be explained by perturbations, which could produce velocities when approaching an infinite distance from the Sun of less than a few km per second. These two parameters are important indicators of 2I/Borisov's interstellar origin. For comparison, the Voyager 1 spacecraft, which is leaving the Solar System, is traveling at 16.9 km per second, 3.570/your. 2I/Borisov has a much larger eccentricity than Oumuamua due to its higher excess velocity and its significantly higher perihelion distance. At this larger distance, the Sun's gravity is less able to alter its path as it passes through the Solar System. Observation. Discovery. The comet was discovered on August 30, 2019 by amateur astronomer Gennady Borisov at his personal observatory Margo using a 0.65-meter telescope he designed and built himself. The discovery has been compared to the discovery of Pluto by Clyde Tombaugh. Tombaugh was also an amateur astronomer who was building his own telescopes, although he discovered Pluto using Lowell Observatory's astrograph. At discovery, it was inbound 3.0 from the Sun, 3.70 from Earth, and had a solar elongation of 38 degrees. Borisov described his discovery thus. 2I/Borisov's interstellar origin required a couple of weeks to confirm. Early orbital solutions based on initial observations included the possibility that the comet could be a near-Earth object 1.40 from the Sun in an elliptical orbit with an orbital period of less than 1 year. Later, using 151 observations over 12 days, NASA Jet Propulsion Laboratories Scout gave an eccentricity range of 2.9 to 4.5. But with an observation arc of only 12 days, there was still some doubt that it was interstellar because the observations were at a low solar elongation, which could introduce biases in the data such as differential refraction. Using large non-gravitational forces on the highly eccentric orbit, a solution could be generated with an eccentricity of about 1, an Earth minimum orbit intersection distance, MOID, of 0.340, 51 million km, and a perihelion at 0.900 around December 30, 2019. However, based on available observations, the orbit could only be parabolic if non-gravitational forces, thrust due to outgassing, affected its orbit more than any previous comets. Eventually, with more observations, the orbit converged to the hyperbolic solution that indicated an interstellar origin and non-gravitational forces could not explain the motion. 2I/Borisov's trajectory was better resolved with a larger observation arc collected from additional observatories. After a 13-day observation arc, a best fit for the hyperbolic orbit had an eccentricity of about 3.5, with perihelion at 2.0. Plan observations. Unless the comet fades or disintegrates unexpectedly, it should be observable until at least September 2020. Observation of 2I/Borisov is aided by the fact that the comet was detected while inbound towards the solar system. Oumuamua had been discovered as it was leaving the system, and thus could only be observed for 80 days before it was out of range. Because of its closest approach occurring near traditional year-end holidays, and the capability to have extended observations, some astronomers have called 2I/Borisov a Christmas comet. Observations using the Hubble Space Telescope began on October 12, when the comet moved far enough from the Sun to be safely observed by the telescope. Hubble is less affected by the confounding effects of the comet than ground-based telescopes, which will allow it to study the rotational light curve of 2I/Borisov's nucleus. This should facilitate an estimate of its size and shape. The observations will serve as a baseline for possible further observations, as the comet approaches perihelion and then leaves the solar system. In the event that the nucleus disintegrates, as is sometimes seen with small comets, Hubble can be used to study the evolution of the disintegration process. Exploration. The higher hyperbolic excess velocity of 2I/Borisov of 32 km per second makes it even harder to reach for a spacecraft than 1I/Oumuamua, 26 km per second. According to a team of the Initiative for Interstellar Studies, a 2-ton spacecraft could theoretically have been sent in July 2018 to intercept 2I/Borisov using a Falcon Heavy class launcher, but only if the object had been discovered much earlier than it was. Launches after the actual discovery date would require a significantly larger launcher such as the Space Launch System, SLS, and orbit maneuvers near Jupiter and near the Sun. By September 2019, even an SLS-class launcher would only be able to deliver a 3 kg, 6.6 pounds, payload, such as a CubeSat, into a trajectory that could intercept 2I/Borisov in 2045 at a relative speed of 34 km per second. According to congressional testimony, NASA may need at least 5 years of preparation to launch such an intercepting mission.